Morning, everybody. Trust you had a good break.
Yeah. Hard to jump right in for anything. We're going to have our exam on Wednesday, as you know.
I want to work through some more problems today. Sort of one last class of problems that involves two bodies.
We had some in the homework like this problem. We'll work this, and if you've already worked on it, I'm sorry, we won't spend too long on it. And then I'll show you a different problem that's similar to number 9, but a little bit different. You should also take a look at number 9 as well. It has some new things in it, but I'll show you in just a moment when we get to that. But let's look at this problem, and then we'll also look at some of the concept test problems at the end. We're not going to have time to do them all, but I've already posted them. I posted them last week, so hopefully you've been looking at them anyway. But if you have questions about those, please do let me know. You can shoot me an email or come by or whatever. I'll be around this week, so please do come see me around all day today and tomorrow. There is a special talk this afternoon at 3 p.m. A professor from LSU is coming to talk about polymer chemistry. I think it's more of a popular talk, where it's going to be fairly low level, but I mean, you can make it support for what's going on. Everybody knows. It's going to be talking about polymer chemistry, and parts. And then there's these 3 years of years. There's 3 o'clock. You might know where it is. I think it's over guard 104. I'm not certain. There's an announcement on the TV screen. You can see me knowledge where it is. Okay. Anything news from the weekend? With the break? Not sure it was long enough, was it? Long enough? So.
All right, let's look at this problem. Again, on the exam on Wednesday, which you'll be able to come at 7:15 like usual, it'll be in Beauregard 165, which is our normal classroom. And I expect we'll be going back there after the exam. I'm pretty sure the projector is fixed now. But on the exam, you won't have two-dimensional problems. That largely means no inclined planes, but also no problems where you have forces at any angle that's not on axis. But like I said, largely that's inclined planes. And we'll pick up that on Friday. We might actually finish it on Friday, but we'll see those type problems on the next exam. Let's look at this problem. Here I have 2 bodies, and I want to know the tension in each rope. Now, as with any force problem, when you come to it, you want to label all the forces that are involved. And so in this case, I have several forces that are involved. I have my weight. I'm going to call this FW1. And so this block will be mass 1, and this block will be mass 2. So I have FW1. I have FT, I'll call this the upper tension, FTU. And that's all that I have on that one. Oh, no, I have another one as well. I have FTB for the tension from the bottom rope. And then for the bottom mass, I have FW2 for mass 2. And then I also have FTB. So on this block, there's a rope in between the 2 blocks. It has a certain tension in it. That tension acts on both the upper block in the downward direction and on the bottom block in the upward direction. So I have FTB here in both cases, acting on both blocks. The next step, you would draw your free body diagram, but honestly, with our one-dimensional problems, you're probably not going to need to do this because it's really just sort of redrawing the vectors. But I'll do it here. This is FTU. These are free body diagrams. I have FW1. I'm just redrawing my vectors on a coordinate system, getting rid of the figure. So there are my forces acting on the top block. I have the tension in the upper string, tension in the bottom string, and then the weight. And then on the next one, I have FTB. That's the tension in the bottom string. And then I have FW2. Now I know the weight, both FW1 and FW2, because FW is equal to M times G. In both of these cases, that's going to be 5 kilograms times 10 meters per second squared, which is 50 newtons. So I can put in FW1 is 50, FW2 is 50 newtons. Now my next step, after drawing the free body diagrams, is I apply Newton's second law. And Newton's second law says that the sum of the forces in either the x or the y direction. In this case, it's going to be the y direction, is equal to mass times acceleration in the y direction. And I can do that for the other one too. The sum of the forces in the y direction is MAY. Or if these forces were acting in the x direction, then we would write the sum of the forces in the x direction as MAX, sum of the forces in the x direction as MAX. But in this case, we don't have any forces in the x direction, so it's just going to be in the y direction. How would I write the sum of the forces in these cases? These are vector sums, and so you want to look at your vectors, ask yourselves which ones are positive, which ones are negative. Positive or negative? This one's positive, it's upwards. Positive or negative? Negative, it's downwards. So I have, writing the vector sum, I say FTU minus FW1, or you can write in the number there if you want, minus FTB equals to the mass, which is mass 1, times the acceleration. Both of these blocks are accelerating at the same rate, so we'll leave that. And in general, on your two-body problems, they will be accelerating at the same rate. And then we can do that for the other one as well. I have FTB minus FW2 equals to M2A. And it's in the y direction. We'll just leave that off since it's not moving in the x direction. Now let's just put in the values that we know. So from this point on, it's really just an algebra problem. We've written our equations, and now we just need to solve those equations. So let's write down what we know. I don't know FTU, but I do know FW1, it's 50. I don't know FTB. I do know M1, it's 5 kilograms. And I think the acceleration is given in the problem. Yeah, it's upwards at 2 meters per second squared. So this is 2 meters per second squared. It is positive because it's going up. If it was going down, the acceleration would be negative. And over here I have FTB minus 50, my weight, equals to 5 times 2 meters per second squared. So now notice that I have two unknowns and two equations, so I can solve these equations for those unknowns. Likely your problem will not include a substitution like we had before. You'll have a problem like that most likely. It'll probably be in your projectile motion section. But this one is fairly straightforward to solve because first I say FTB equals 50 plus 10. That's equal to 60 newtons. And then I can take that and plug it in over here and solve for FTU. I get FTU equals 50 plus 60 plus 10, which is 110, 120 newtons. So that's FTU, and that's FTB. That'll be the general procedure that you'll take on any of these problems. You will have a two-body problem. You'll have a one-body problem too, like some of those other homework problems that I pointed out to y'all last time, and I'll show y'all again what those are in case you didn't get it. But you'll also have a two-body problem in one dimension. In the next exam, we'll have a two-body problem in 2 dimensions, and it becomes a little more complicated. Let's work one more, okay? One that's not in the homework, but this is also a good example. And number 9 is also a good example. Well, let's take a look at another problem. You should have a blank page right before the homework. Oh, wait, no, you don't. You have one after the homework? Yeah, you have one after the homework, a blank page. So let's imagine that we have a surface and we have two objects. We have one object, I'll call it mass 1. It has a mass of 10 kilograms. And then I have another object, we'll call it M2. And it has a mass of 20 kilograms. have a force pulling it over here, and these two objects are connected by a string. So a lot like the previous problem that we had, except now we're going to throw in some friction. Let's say that mu k is equal to 0.1 for both objects. Remember, mu k is the coefficient of kinetic friction. With friction, we have static friction and kinetic friction. Static friction is when the objects aren't moving. It has some maximum value. Once you reach that maximum value, after you exceed the static friction, then the object starts moving, and then you take into consideration kinetic friction. Just to remind you, my kinetic friction, Fk, is equal to mu k times the normal force. Let's say that these objects are accelerating in the positive x direction at 2 meters per second squared. So I would write that as plus 2 I meters per second squared. Or I could just say moving in the positive x direction at 2 meters per second squared. But the I there means in the positive x direction. Okay, so that's my acceleration, and I want to know what is the force. What is that force that's required to move them in that direction? Now, this problem is complicated because I have two different frictional forces. I have a friction over here and a friction over here. Because these are different masses, they're going to have a different friction. Why don't you begin by writing all the forces that are involved on this block, drawing them on your finger. You have 1, 2, 3, 4 forces acting on this block. And then also writing the forces here. I already have one of them, but then you have 1, 2, 3, 4 additional forces there. So go ahead and draw all your forces that are acting on the blocks. You should have 4 each. Give you about a minute. First block, I have my normal force, Fn1, and my weight, I'll call this Fw1. In the x direction, to the left, what do I have? The frictional force. To the left, in this direction, I have, I'll call it Fk1, because it's the frictional force acting on mass 1. And then what do I have to the right? Dustin, I think you said it. To the right, what do I have? I have the tension force, right? So my tension is going to, I'll just call it Ft, because the tension in the string is the same for both blocks. A tension is a tension. It's not going to differ for either of the blocks. And how about this second block? What are the forces that I have? In the y direction, it's going to look exactly the same. I have Fn2, and I have Fw2. To the left, what are my force or forces? Tension and friction. Remember, the friction always opposes the direction of motion. And so since this thing is moving to the right, my frictional force will be to the left. So I'll call this Fk2, and I'll call this Ft. This is Ft. Notice these two forces are exactly the same, because a tension is a tension. The tension will act on both of the objects. And then on this side, on the right, I have the force, F. And that's the force that I want to know. I want to know what F is. Now we have forces that are acting in both the x and the y directions, and so I can write Newton's second law. So what you need to do now is write the sum of the forces in the x direction equals what? And the sum of the forces in the y direction equals what? Now in one of these directions it's static, and then in another direction it's a dynamic problem. It's moving in one direction, not moving in the other. And write your vector sum there for the x and the y directions. In the x direction, I'll have ft. Remember, this is my positive x, this is negative x. Ft minus fk1 equals to, is it equal to 0 or what? Or not 0? It's not 0, because in the x direction it's accelerating. So you need to be careful here. It's going to be m times a. But you need to be careful because this needs to be m1. The reason this is m1 and not just m or m2 is because when we write this equation, we're not even thinking about the second clock at all. And so when I write this, I'm only concerned with the first clock. So I always include m1, not m2 or m. You need to be very careful with your subscripts when you're writing these equations. They got a bunch of m's. Next on the 2D problems, we'll have to have different accelerations too. And so we'll need to, show our different accelerations. But our m1 here is different from our m2 that we'll write on the next side. In our y direction, it's a little simpler, because I have fn1 minus fw1. That's equal to 0. It's equal to 0 because it's not accelerating in the y direction. All right, we can do the same over here. We can say the sum of the forces in the x, sum of the forces in the y. In the x, it's going to be f minus fk2 minus ft equals to m2 times a. The sum of the forces in the y is just like we had before, except fn2 minus fw2 equals to 0. Okay? There's one other little piece of information. I wrote it before, I'm going to write it again, and that is that fk is equal to mu k times the normal force. So you can think of that as a third or even a fifth or even a sixth equation. But so far what we have here is we have 1, 2, 3, 4, and then this extra little equation up here. Now it becomes an algebra problem. I want to know what f is. I want to know this. But I don't know this. I don't know this. I don't know this, or this, or this, or that. So there's a bunch that I don't know, and so it might seem insurmountable to solve this, but it's actually not. So first of all, we're going to look at these equations. My normal force is equal to my weight in this case, and I do know what my weight is in both cases. So let's look first at the y direction. My normal force is equal to Fw1, which is equal to m1 times g. And my first block was 10 kilograms times 10 meters per second squared. That's equal to 100 newtons. Similarly, over here, I can say Fn2 equals Fw2, which is 200 newtons. That's 20 kilograms times 10 meters per second squared. Okay? So that's our normal forces. Now that we know our normal forces, I can also calculate which force. If I know my normal force, that's related to which of the forces that's at play here. The frictional force is Fk. So I can go ahead and solve for that too. I can say Fk1 is equal to mu k times Fn1 being very careful with my subscripts. I know that's where some of you are going to mess up with your subscripts. You're going to forget to write your subscripts, or you're going to write your subscripts incorrectly. And then when you're actually in this part of the problem where it's just an algebra problem, you're going to get confused about which forces are involved where. So when you're writing these equations at the beginning, just be very careful with your subscripts. Be very careful with your vector diagrams. That's why it's important to make sure that you label these vector diagrams very carefully. Okay, so mu k times Fn1, that's 0.1, that's my coefficient, times 100 newtons. That's equal to 10 newtons. And then similarly over here, I can say Fk2 equals 0.1 times 200, which is equal to 20 newtons. So now I know a whole heck of a lot more than I did before, because now I know my kinetic friction, and I can return back up to these equations. I'm going to rewrite them, but now with the values that we actually know. So I know Ft minus Fk1, that's 10 newtons, equals M1A. That's going to be 10 kilograms times the acceleration. And I gave the acceleration. Did I give y'all the acceleration? What is it? It's equal to 2, right. It's equal to positive 2. And then likewise, I can write for the right-hand side, F minus Ft, I don't know Ft, minus Fk2, that was 20 newtons, equals to 20 kilograms times my acceleration, which is 2 meters per second squared. What I've done here is I've taken these equations and I've just put in the values that we know. These are the sum of the forces in the x direction for both blocks. Just put in the values that we know. And then you can probably look at this and see, oh gosh, this isn't that hard, because now I can solve for Ft. So once I know Ft, I can solve for F. There's no substitution required. I just want to first solve for Ft and then solve for F. It's not a simple problem, but it doesn't require substitution of one equation to another, which can get a little messy. So I have Ft is equal to 10 plus 20, which is 30 newtons. That gives me my Ft. And then I have F is equal to 30 plus 20 plus 40 equals 90 newtons. So that is the answer. That's the force that's required. You shall have a two-body problem acting in one dimension. It'll be either vertical or horizontal. There's not a whole lot that I can do to that. There are some slight complications, like I could have extra forces pushing in the x or y direction, but it's not going to be a whole lot different from this one or the elevator problem. Number 9 is a little bit different. I'm not going to work it here. Some of you might have already worked it. Number 9 and 10. Number 9 is different because here I have a spring constant. We haven't talked about springs. In fact, we don't really cover springs in this class at all. But the only thing that you need to know I give you in this problem, and that is that the force due to a spring is given by this F equals Kx. So the force due to a spring is equal to Kx, not Kg, Kx. The more you stretch a spring, the more the force it exerts. So on this problem, you would have my force due to the spring is equal to K, that's a constant, times the elongation of the spring. And similarly over here, the force due to the spring is equal to Kx. They both experience the same force, much like when you have a rope between the two objects. And that force is equal to K, which is the spring constant, it's given here, times the elongation of the spring. This complicates the algebra of the problem, because it gives you an extra unknown here. I'll leave you to look at this, but you should certainly take a close look at it. You could see something like it on the exam. Okay? Have y'all looked at that problem? Anybody? Not yet. That's okay. Some of you have. We have a couple days until the exam, but please do take a look at that one in number 10. And also, just to remind you, I circled them before in class, but there were number 7,
number 4, number 3, number 1, number 2, I think. Yeah, number 2. Those are all one-dimensional problems, 1D problems. Okay? Let me just sort of summarize what's going to be on the exam on Wednesday when you come in. And we have Chapter 3, all of Chapter 3. So you will have a vector problem. Now, let me just tell you, if you've been in the lab, it's going to be a lot like that vector problem, where I give you the numbers for the vector. I say one vector is 20 newtons at 5 degrees from the x-axis, and one vector is so many newtons at so many degrees from the y-axis. And you have to find the vector sum. So you will have to do a vector sum numerically. And then I'll also ask you to sketch out the vectors. You don't have to do it like you did in lab where you have to create a scale and do it all to scale, but I'll just ask you to sketch out the vectors. It's good at practice anyway, but because it helps you to verify your answer, because you can see, the rough direction of the sum, and it's just a good practice to do that. But you need to do it numerically, and then I'll also ask you to sketch the vectors. So these are just the free response problems I'm talking about, but you will have to do a vector sum. You will have projectile motion. You'll probably have 2 problems for projectile motion. One will be simpler. You start at one point, you end at the same horizontal, same vertical height, something like that. We've worked those in class, and you have some in the homework. One will be more complicated algebraically, where you're missing some information, like ones that we've worked in supplemental problems, or in your homework, or even in class. So something akin to those. Make sure that you look at those problems and you can do them well. They won't be identical to those, but they'll be very similar to those. So you'll probably have 2 projectile motion problems. Probably, maybe not, but fairly certain you'll have 2. 2 of those. One that's more straightforward, and then one that mathematically at least is more difficult to solve. You might need to use the quadratic equation, but if you do have to use it, I'll give you the quadratic equation. Okay? But just go back and look at it, make sure you're familiar with it. We used it in class. And then you'll have some 1D force problems. You're likely to have 2 of these. One will be a 2-body, like these that we've seen today, and one will be a 1-body problem, like some of the homework. Like number 1, like number 2, like number 4, a 1-body problem. You can see either static or dynamic problems. So static problems is where that acceleration in Newton's second law. Static is when this is equal to 0. And then this dynamic is when it's greater than 0. And we've done both, but it's just a matter of do you set your acceleration equal to 0 or not. So that's 5 problems. That's probably that will be what you see. 1 vector sum, adding up 2 vectors. Nothing fancy, probably 1 off-axis, 1 on-axis, just like in the lab midterm. And by the way, if you haven't had your lab midterm, it shouldn't be a surprise to you. They all have different lab midterms, so I don't know what yours will have, but it shouldn't be a surprise to you, because on the old midterms, they always have that. 2 projectile motion problems. One, probably just, you take a ball at 30 degrees with some velocity, how far does it go, how high does it go? Kind of like the gone in 60 seconds problem. That's sort of the archetypal projectile motion problem. And then one that's more complicated, kind of like the supplemental problems, are like some of those in your homework. Then 2 1D force problems, 1 2-body, 1 1-body. This one and the more difficult of the projectile motion, they'll be worth more, 10 to 15-ish points, and the others will be worth more like 10 points. Okay? Any questions about what to expect for the exam? What equations are we responsible for? There's not an equation sheet on this, but let me summarize them, because there aren't really that many. I know it seems like there are a lot, but in practice, there aren't really that many. We have our kinematics equations. We have y equals v naught y t plus 1/2 ay t squared. We also have vy
equals v naught y plus ayt. Those are our kinematics equations. They're from chapter 2, except we've made them specialized for our projectile motion. So in addition, we also have this x equals vxt. That's really just this equation right here with two small changes. We take this out because ax equals 0, and we take this out because vx is equal to v naught x. Vx velocity doesn't change. So we can just write it as this. That's for projectile motion. You also need to know your x and your y components. Vx equals v naught cosine theta. Vy equals v naught sine theta. In general, you need to know how to find your x and y components. That's also true for the vector problem that you have, the vector sum problem. And then for chapter 4, well gosh, you really just have this. Sum of the forces equals ma. That's true in the x and the y directions. I think that's all that we have here. If you have the spring, like in chapter 9, I'll give you that equation on the exam, because we haven't covered that. I think that is everything. Oh, and then also the frictional forces. Fs is greater than or equal to mu, or excuse me, less than or equal to mu times the normal force, and Fk is equal to mu times the normal force, mu k, mu s. I understand that it seems like a lot, but it's not really that much, because these two are just our kinematics equations from chapter 2. We've been dealing with these a lot. This one is just an adaptation of one of the kinematics equations. These are our vector components, and then here, Newton's law, Newton's second law, and our frictional forces. It's a good question. On the next exam, you'll begin to have an equation sheet. We get more and more equations as we go along. But up to this point, I think we're okay. Okay. Anything else? Any other questions? Yeah. Which, well, I don't think we need to. Okay. Let me just address it separately, because I don't think we need to go back to the problem. So in projectile motion, by the way, you'll have a problem like this, where you start at one point, end at the same point, find the maximum height, find the maximum range. Make sure that you can do it. It'll be an easy, not easy 10 points, but it'll be 10 points you can depend upon. All right, so remember, we start out with an initial velocity, but we can break that velocity into its x and its y components. And so here, this is my y component of that velocity, and this is my x component of that velocity. As I move through the trajectory, because ay is equal to negative 10, my vy gets smaller. So here Vy has some value. Here Vy is equal to 0. This is just like if you take something and you throw it up in the air, and in the top, it stops at the top of the trajectory. And then it begins to increase in the negative direction. So over here, if V naught y was, say, equal to 10 meters per second, over here, Vy is going to equal to negative 10 meters per second. We had that problem in the previous test, I think. Pretty sure if it leaves here at 10 meters per second, it goes up, it comes back. It has a velocity of negative 10 meters per second. Same magnitude, but different direction. It's my y component. It gets smaller. It goes to 0. We often use this fact, the velocity at the top is 0, to solve for the time, because we can find the time at the halfway point using this fact. Nicole? Is that a little helpful? No? Okay. Don't forget too, the velocity in the x direction doesn't change all the way throughout the trajectory. Any other questions or nagging problems? Okay. I don't think that, I mean, it's going to be a tough test, of course, because they're all tough in their own right. But since we're not doing 2D force problems, it's a little simpler. But the projectile motion, that's going to be the tough one. That's sort of the toughest part of this whole exam. The two body problems too, you just need to spend some time with that and make sure that you're aware of how to set up your vector diagrams and then how to solve those equations, how to write the equations. When you're writing those equations, just a hint that you need to be very careful with your signs and with your subscripts. And just once you get to that point, I consider that most of the problem. If at that point, if you mess up solving it, I'll count off a point or maybe two, depending on how bad you mess up solving it. But be very careful that you write your equations properly at that point. Let's just look back. Okay, nothing's standing out to me. Do make sure that you remember how to write these velocity and position versus time graphs for the projectile motion. I could ask you for something like that. For any part of the projectile motion, for the first half of the trajectory, for the last half of the trajectory, make sure that you understand what these graphs mean and how to draw them for a motion. Okay, and as I said, you'll have to do a vector sum, or maybe a vector difference as well. A plus B, A minus B, that sort of thing. All right, I think that's it. Let's take a look at the concept test. We're not going to answer all these in class, but let's just take a look at some of them in our last minutes of class. We've done a lot of these, right? Or we've done maybe a third of them. To what point did we get up to? Right now? 4.4a. These are online on the, oh yeah, so let's do a couple of these. Oh, by the way, there is chemistry majors. There is like a meet and greet type thing. Have y'all heard of this? Who's my chem majors? It's at 11 a.m. You might verify. Nobody's heard of this? A pizza thing with the guy? Okay, let me check my email. Right, just give me 20 seconds while I check that before I tell you incorrectly. Yeah, today's October 3rd. At 3 p.m., this guy, Dr. John Pohman, one of our graduates actually was his PhD advisor, Leah Garber. I don't know if y'all know her. But he's going to be here at 11 to meet with you in the Beauregard conference room, and there'll be pizza for you. He wants to meet with y'all just sort of to talk about, opportunities at LSU. I think he's a pretty nice guy. He's not mean, like me or other people in the department. But at 11 o'clock, and you get to eat pizza. So it's only open for chemistry majors, but go at 11 a.m. in the conference room. It's right across the hall from where our classroom is. Okay? Should be a good opportunity. Okay, so let's look at this. From rest, we step on the gas of our Ferrari. Should have did the answer. Well, I'll show you the answer here. So I step on the gas or a Ferrari for 4 seconds, speeding up to the final speed v. If the applied force are only half the original force, how long would it have to be applied to reach the same final speed? So a couple of things going on here. That F is equal to m times a, and v is equal to v naught plus at. In this case, v naught is 0 because it says from rest. So if I have a force, then that gives me a certain acceleration, and then that will provide a certain velocity. And it says here that I get up to a speed v in 4 seconds, providing this force. But then what if I have this force? What does that do to the acceleration? It halves the acceleration. If I have half of this value, it's a direct proportionality, so I have this value. If I have this value over here, then I have to double my time in order to get the same velocity. And get my clicker face up here. We'll try this one. Y'all try this one on your own. Well, we'll try to get. Force acts on a mass m for time t, given a final speed v. What if the force acts on the same time but on a different mass? What would the final speed be of the bigger mass? All right, I'll stop at 38. Okay, good. D is right. If I have a force that acts on a bigger mass, that means I'm going to have a smaller acceleration. And if it's half the mass, well, F is equal to ma. If I have twice the mass, then I have half the acceleration, given a constant force. And so the final speed, if I have half the acceleration, if this is half, then this is also going to be half. So D is the right answer. I'm going to show you this one. Oh, y'all try it on your own. Go ahead and try it. Force acts on a block M, giving it acceleration A1. Force acts on a block M2, giving it twice that acceleration. So ask yourself, how do these masses differ if I get twice the acceleration? Now what if the same force acts on the two blocks together? What will be the acceleration in terms of A1? All right, I'll stop at 115. Okay, we're a little bit all over the board here. Pretty sure E is right. Let's just double check. So here, my F equals ma for this one. Here, when I have twice the acceleration, that means that M2, is it bigger or smaller than M1? Smaller. By what amount? It's half the mass. So I have half of M1 here. And then if I put the two together, it's like M2 plus M1 this is equal to 3/2 the mass of M1, because I have M1, and then I have half M1. So the 1.5 M1s are 3/2 of M1. And so if my force is acting on 3/2 of M1, then that means I have to have 2/3 of A1 as the acceleration in order to give us the same as what we had up here. So E is the right answer. It's a tough question. See, a lot of you put C. I think were you just guessing for C? Sort of, maybe? I think so. It's kind of a tough question. But take a look at it. In fact, all these that are dealing in one-dimensional problems, you need to take a look at for the test coming up Wednesday. Just do a few more. This is the force due to gravity. The weight is equal to the mass times the acceleration. So the weight of a stone is bigger than the weight of a feather just because it has more mass. But the acceleration is always the same. That's our value for G, for both of those. Let's try this one. This is 4.9a. Block M rests on the floor of an elevator. It's moving upward at a constant speed. What is the relationship between the force due to gravity and the normal force on the block? Is the normal force bigger than the weight, equal to the weight, less than the weight, equal to 0, or does it depend on the size of the elevator? Very good so far. Ask your neighbor what you put. Only about 15 of you have the right answer right now. Not half of you. So ask your neighbor what they put. It is moving upward at a constant speed. Make sure you read that and understand what that means. I'm going to stop at 115. Okay, good. B is equal to B. Our normal force is equal to the weight. You might have been, and 4 of you were, you might have been inclined to put A here, that the normal force is bigger than the weight because it's moving upward. But also notice that since it's moving at a constant velocity, that means the acceleration is equal to 0. So if the acceleration is equal to 0, the normal force will equal to the weight. Let's try this one. Very similar problem. Okay, very good. I'll stop at 35. Okay, awesome. A is right. Here it's accelerating upward, so the normal force is bigger than the weight. You can think about your forces. I have my normal force. I have my weight. I can write the sum of the forces in the y direction. That's Fn minus Fw equals MAY. And so my normal force will equal to Fw plus MAY. So my normal force is bigger. Normal force is bigger than the weight by this amount. All right. Hey, listen, y'all get this now. 2 cats slide off a roof, or 2 cats are on a roof. Which one slides off first? And you say, I don't know which one. The one with the smaller mu. Like the coefficient of friction slides off first. That's a good one. Okay. Alright, we're going to skip this for now. We'll skip this one. All these inclined plane problems, we're going to skip this one too because we skipped that. In fact, I think I'll let y'all, we'll wrap up there. And these are already online. Take a look at them. Most of the others are not nearly complicated. So take a look. You see the problem numbers. Okay, look. 3 more exams. We're almost to midterms. This is midterms, right?